Hello, and welcome to an entire chapter dedicated to thermodynamics. I'm so excited. I love this material, and it's not usually something that you hear people say. They don't usually say, oh, thermodynamics, I love it. But there's so much neat stuff in this chapter. There's so much detail about how the world works, how the universe works. We get to really explore the entire universe in this chapter, which is really cool. You want to understand why things happen, you have to understand thermodynamics. So I've got the overview here: spontaneity, entropy, systems and surroundings, free energy, reactions. How are these all related? I've got exclamation points on them because this actually really is exciting material. It's not easy material, but it's exciting material, okay? We get to talk about standard conditions, non-standard conditions, these little circles and stuff that people write. K's and delta G's, are they the same thing? And potentially they are, but you're like, I don't know what delta G is. Or maybe you do. You've seen it before, you haven't seen it before. It's okay, we're going to talk through this. A lot of this chapter, especially the front-loaded stuff about entropy, is a lot of detail. I go into very, very good detail about what entropy is, why are we studying it, why do we care, what does it really predict. At the end, there's just a few equations that we use in terms of numerically getting entropy. And those are actually relatively straightforward. But the concept itself is difficult to grasp, but it's really, really exciting. So that's what we're going to be working on. Now, I'm going to start you, because most people think thermodynamics and they go, oh, my life is over. I'm going to start you with a quote from a person who wrote a textbook on thermodynamics. And it is this. To me, thermodynamics is a maze of vague quantities, symbols with superscripts, subscripts, bars, stars, circles, getting changed along the way, and a dubious method of beginning with one equation and taking enough partial differentials. We don't do partial differentials in this class, but there's a lot of those in thermodynamics. Until you end up with something new and supposedly useful. And if that doesn't work, you try graphing. We might do some graphing in this class. I have the impression, however, that to other people, thermodynamics is a logical study of the effects of temperature and pressure on matter and energy. And we'd like to get there, but it's hard, right? This guy wrote a thermodynamics textbook. Obviously, he was saying this a little bit tongue-in-cheek, but there's a truth to it. There's a truth to the difficulty of this material to understand. But like I said, the application of it, the actual math, pretty darn simple. Addition, subtraction, a little bit of algebra going on, not too hard. But why? What does it mean? That part does take a while to grasp. Another quote that I didn't write down was from one of my college chemistry teachers. Hi, Professor Baker. And she said this. She said, well, when you're when you first take chemistry, you take some thermodynamics and you have no idea what's going on. And then you go on, if you're a chemistry major, you're going to take a course called physical chemistry, where you study thermodynamics in more detail. And when you do that, you finally understand the thermodynamics that you learned in freshman chemistry. You're like, oh, great, I finally understand that stuff. But then you don't really understand the stuff that you learned in physical chemistry. And then you go on to graduate school. And you take graduate level thermodynamics and you're like, oh, I finally understand that thermodynamics that I learned in physical chemistry, but you don't really understand the graduate level thermodynamics. And she's like, and actually, it turns out in the world, no one understands graduate level thermodynamics, right? And this is a person who did thermodynamics for a living. So we joke about it because we like it, but it's also a weird concept to think about some of this stuff. So we're going to go through it. We're going to talk about it. We're going to talk a lot about the why and all sorts of details. And hopefully by the end of it, you're at least have minor understanding, a little bit of understanding of what this is and why it's important. But like I said, you'll probably have to take it again someday if you really want to understand the stuff you learned here. Okay, so our goal. Right now, what we're going to be talking about is spontaneity. And what does it mean to be spontaneous? If you're like, oh, I'm such a spontaneous person, what does that mean? It means you do kind of stuff all the time. Like, stuff just happens, right? It happens spontaneously. No one's making you do it. No one's forcing you to do these things. And that's actually a good technical definition of spontaneity. Spontaneity is something that happens without outside intervention. If I were to take a bottle and let go of it, right, it would fall because of gravity. And the gravity would not be me doing anything in outside intervention. I just let go of it, right? And if there wasn't something happening, right? If there wasn't some spontaneous reaction, it would just float there. But the spontaneous reaction is that it falls due to gravity. So there's some spontaneity there. Okay. Now, spontaneity doesn't tell us anything about how fast it happens. It just tells us that it will happen eventually. And that should sound a little bit like our equilibrium type of problems. And so it turns out we will be relating all this kind of stuff back to equilibrium towards the end of this chapter, which is really kind of cool. So, stuff that happens without outside intervention. So, if you've looked at the world, right, you say things rust. Right? So that happens without outside intervention. You just leave some metal there, boom, it rusts. But what you've never seen in your life is you leave some rusted metal there and boom, it unrusts. Right? So there's a spontaneous direction, right? It's spontaneous towards the rust, but not towards the unrust. Or maybe you've seen something dissolve, right? You take some salt, you stir it into some water, it dissolves. But you've never just stirred some salt water and be like, poof, poof, some salt undissolved. Now, it's different than precipitation, right? That's a very different type of chemical reaction. But you've never seen salt undissolve in a solution where it's already dissolved. Now, yes, you can evaporate the water, you can make it dissolve, but that's outside intervention. So there's a direction to spontaneity, right? One direction, things are spontaneous. The other direction, they aren't. Things rust, but they don't unrust. Things dissolve, but they don't undissolve. So that's an interesting thing to think about spontaneity. Now, why? Why are things spontaneous is a great question. Why does this happen? Why does rust happen, but not unrusting? And our analogy that we're going to use is gravity, the one I used right here with my little bottle. So what's gravity got to do with it? Well, if I take a curve like this, and I put a little ball right here, and it can roll, it's a rolling ball, right? We all know that it's spontaneously going to roll down that hill. Now, why is it rolling down the hill? What is it trying to do? Well, it's trying to actually decrease its total potential energy. If this is an energy graph on the y-axis, then it's trying to decrease its total potential energy, and so we have the ball trying to go down to the bottom. Now, of course, it converts its gravitational potential energy to kinetic energy, so it goes back up the other side, and you'll see it go back and forth and decrease over time due to friction and things like that. But really what it's trying to do is get down here, because down here it's at the lowest possible gravitational energy. So it's at its lowest possible gravitational energy, and that's what it's trying to do. Now, what about a chemical reaction? What is it trying to do? What kind of energy is it trying to decrease? Well, we've looked before at these graphs of energy versus reaction progress. Right? Also called the reaction coordinates sometimes for people who are a little fancier sounding. And we said, oh, look, we start with our reactants. There's always some sort of activation energy. And here we have an endothermic or exothermic reaction. Which is it? Endo-exo. What is it? Okay. What do you think? Good. Hopefully you came up with exothermic. Somebody was calling. I mean, there was people calling my show to say, it's exothermic, it's exothermic. Okay. So exothermic is hopefully what you came up with, because we have less energy at the end than we did at the beginning. That energy's got to go somewhere. It goes out into the world. So we have an exothermic process here. And we're like, okay, well, that's kind of what it's doing, right? If we think about the marble analogy, right? If we give it enough energy to get started, eventually it will roll down that hill and try to get to that endpoint. And in fact, we have a lot of evidence for this. We have lots of exothermic reactions in the world that are spontaneous, right? You take some methane, you light it, you burn it, it'll burn forever as long as you've got that source. So it's kind of a spontaneous reaction. It doesn't require that outside intervention once you get it going. But that would imply that there's never going to be a reaction that's endothermic and spontaneous, because that would be going uphill and we wouldn't be getting to the lowest possible energy. We'd be getting to a higher energy, and well, that's not right, is it? So are there any reactions that are endothermic and spontaneous? And you're probably like, well, I can't think of any off the top of my head. But it turns out you've run across them before. You've probably, maybe once in your life, gone to the store and bought one of those icy hot packs, right? You break it apart, And all of a sudden, what does it do? It cools down. How does it cool down? Well, because there's a reaction in there that's endothermic, that's absorbing heat from the surroundings, right? There's no such thing as cold. There's just things loss of heat. So it's absorbing heat from the surroundings. And that endothermic process is spontaneous, right? Once you mixed those chemicals, right? That's what you did when you kind of squished it, is you just mixed those chemicals. It made a spontaneous reaction, and it was endothermic. So that kind of counters that argument. We can't say, oh, delta H, our enthalpy, is that thing that's driving reactions. We're going to try to get to the lowest possible enthalpy. Certainly, it's related to it, because we certainly find a lot more exothermic reactions that are spontaneous than endothermic reactions that are spontaneous. But it's not the end-all be-all, because we can find a counter-argument. Okay? So what is it? What is it that drives the universe? Right? That's what we're going to talk about next. The entire universe. Like, whoa, whoa. Like, everything that happens in the universe can come down to this one statement. Everything in the entire universe can come down to this one statement. Is it going to happen? Is it not going to happen? Now, how do we come up with this one statement that I'm about to give you? Well, some people who are like smarter than everybody who ever watches this video and me all combined together worked on this for years and years and years and years of their life, sometimes not finishing it and passing it on to the next generation. And then finally, they came up with what we're going to talk about here. This wasn't just like, oh, somebody was like, oh, yeah, of course, it's this. Duh. Like, we kind of treat it like that now. Like, oh, of course, it's just obvious. But it wasn't when people didn't know it. Right? A lot of things in the world seem obvious once you know them. Right? So you're going to hear people talk about thermodynamics all the time. Like, oh, well, this is just it. You calculate this, you calculate that. But it was really hard to figure out the first time. Really hard to figure out. But eventually, a bunch of really smart people came together. They figured this thing out. And we're just going to take it as true. Okay? We're not going to try to prove it or anything like this. And it's this, that an increase in the entropy, and we're going to have to define that later, but we're going to use it for now, of the universe is the sole criteria for spontaneity. The sole criteria. All you have to know is, did the entropy of the universe increase? Like, oh, yeah, it's so easy to calculate something about the entire universe. Wow. How do you calculate something about the entire universe? I mean, seriously, to know whether this pen falls or doesn't fall when I let go of it, I have to know if the entropy of the entire universe increases. I mean, that's like Mars, that's like planets far away and stars. And I have to know whether their entropy increases in order to know whether this pen falls. I'm like, can't I just say, hey, look, I'm used to the pen falling? Yes, right, we know that, right? But how can we prove that? Scientists are crazy sometimes. Like, hey, let's prove the things we already know. Why do we prove the things we already know? So we can prove things that are harder to see, right? So we can prove those things that we can't see, that we can't visually experience. We can say, oh, I know this is going to happen because I proved it, and I proved it for these other things. So we're going to take that at its word. But the first thing we have to figure out is, what is entropy, right? We need to know what is entropy before we can really understand how that entropy is the sole criteria for spontaneity. But that's it. If you can say, hey, I'm about to do something and the entropy of the universe is going to increase, then that is a spontaneous process. If you say something's about to happen and the entropy of the universe is decreasing, it's not going to happen, period. End of story. Like, really. Like, if you can say, this happening would decrease the entropy of the universe, that will never happen. Pretty cool. All right, so check in. A reaction that is spontaneous will always, like always is in italics there, right? Happen without on-site intervention, release heat, increase the entropy of the universe, or have more products than reactants. Or both A and C, A, B, and C, or all of the above. Go! What do you think? Well, we actually talked about one of these just a slide ago. Well, a slide ago, 2 slides ago. Anyway, and we said, hey, look, we're used to exothermic reactions being spontaneous, but that is not always. That's not everything, because there's endothermic reactions. So we know it's not B, and we know it's not those, because those contain B. So what else happens without outside intervention? I think that was basically the definition I gave you of spontaneous. Increases the entropy of the universe. That was the criteria for spontaneity. In order for something to happen, increases the entropy of the universe. Awesome. And then have more products than reactants. We think that sometimes. We're like, oh yeah, if you're making more stuff, but no, nothing to do with it, okay? It's not related to that. All right, so it turns out it is both A and C, so you've sort of gotten E. All right, so now let's talk about entropy. What is entropy? Now, we could just go into a straight definition of entropy. I could give you equations and tell you this is a microstate environment, but let's just think about it first, okay? Let's actually talk about some examples and things like that and try to figure it out. So I've got a box. Hey, look, I'm in a box already. Look at that. Okay, I've got a box, and in that box there's dots. There's dots, dots, dots. And what I want to know is this. The dots are gas molecules. What's more likely? That the air molecules in the room are spread out in those exact positions. So this dot is here, this dot is here, this dot is here, and we know that exactly. Or the air molecules are all kind of shoved into one corner with everybody exactly here, exactly here, exactly here, exactly here, and exactly here. Now, most of you would probably go, well, it's the one on the left, because you've never in your entire life had an experience where you've walked into a room and been like, where's the air? I gotta find the air. Oh, excuse me, I've got to go breathe. It's over in the corner. Let me go. And so you breathe from one corner of the room, then you move around. You go like, okay, I gotta find the air again. Oh, it's moved to the top corner. And you breathe from the top corner. You've never done that in your entire life. Every time you've ever walked into a room in your entire life, the molecules have been spread around the room. So you're like, gosh darn it, that's gotta be the more likely arrangement of molecules. And it's not. I'm going to tell you, and then I'm hopefully going to show you, that these two are equally likely. That you are just as likely to find the molecules at those exact positions on that left box or those exact positions on that right box. Now, I'm very specific about my wording. I said those exact positions. Okay? That's going to be pretty important as we move forward. How can that be? Well, let's simplify things a little bit, because talking about a giant box with molecules that can move all over the place is a really hard place to start. So let's talk about two little boxes. So we're talking about almost like a quantum system, right? We've got a box on the left, a box on the right, and the dots can only exist in those little boxes. They can't exist in the little tubes in between. I'm going to start off with my red dot and my blue dot on that left-hand circle there. I'm going to open up the thing, and let's think about all the different ways that this system can arrange itself, right? Now, I'm going to cheat. I'm going to use R and B instead of drawing a red ball and a blue ball, just to make my life a little bit easier. Okay, but I will use a different color entirely. I'll use black so that we aren't confused. Okay, so if I open up that thing, a few things can happen. One, nothing. Red and blue are just on the left. Another, red and blue are both on the right. Another, red is on the left and blue is on the right. And another, blue is on the left and red is on the right. Those are the four possible arrangements of my dots, right? If those are the only places that they can exist. Now, of course, because this is chemistry, we have language for this. Okay, we have language that talks about all the different possible arrangements. So all the different ways we can say, hey, the system looks like this. Like it looks like red, blue on the left. Or the system looks like this. It's red, blue on the right. Those are called states. And when you know the state of something, you know everything there is to know about it. Now, we've simplified this system a whole lot. And we've said left, right. Those are the only things that can be, left, right, red, blue, I guess. Those are the only things that can be known about my system. In real life, all sorts of stuff can be known about your system, right? How fast it's going, where it is, its arrangement, what the arrangement of the electrons are. I mean, there's almost an infinite number, not exactly infinite number, thank goodness, but a huge number of ways we can talk about all those different things. But if we know everything there is to know about a system, then we can call that, oh, that's its state. Or we can say it's in this state even though we don't know everything, but let's assume we know everything. And sometimes people talk like that because it really is impossible to know. Okay, so we know everything about every single atom, every single electron, everything in that system. And that would be a state. Okay, now what we're going to do in the next slide is we're going to distinguish a little bit because there's actually different kinds of states that we're going to talk about. So we have 4 arrangements of this particular system. That means it has 4 different states. So let's increase the size of our system by just 1 dot. Still 2 balls, 1 dot. Things can be on the left, things can be on the right, but now they can be red, green, or blue. Let's open that thing and arrange it, right? We can get RGB over here. We can get RGB over here. We can get red and green on the left and blue on the right, or we can get the mirror of that, red and green. We can get red and blue and green, green, red, and blue. And we can get green and blue and red, or red and green and blue, right? So those are all the different possible arrangements, all the different possible states. So how many states are possible in this system? Is 8, right? We have 8 possible states in this system. And that's if we know everything, right? We know the color and we know the position. Now, what we're going to say is, let's be a little more specific. If we know everything about it, color, and we can identify each one from each other, we're going to call those microstates. Right? Microstates. So this one actually has 8 microstates, and that's when we can distinguish particles. Right? We know everything about every one of them. We know its colors, and so we can distinguish them. But what if we couldn't distinguish color, right? What if we couldn't tell the red, green, and blue? We could just tell it was hydrogen, right? It's just there's hydrogen over there. Right? Can you tell hydrogen 1 from hydrogen 2 from hydrogen 3? Not really if they're identical, right? And so instead of having RGB, now we just have AAA, right? There's just 3 things on the left, or there are 3 things on the right, or maybe there's 2 things on the left and 1 thing on the right, or 1 thing on the left and 2 things on the right. But if you look at these other arrangements, right, they're just duplicates of these if I don't know the difference between red, green, and blue, right? Either my arrangements are 3 on the left, 3 on the right, 2 on the left, 1 on the right, 1 on the left, 2 on the right. Those are my all different things. So it turns out that I only have what we call 4 macrostates. And here we cannot distinguish particles. They all look the same to us. There's no red, green, blue. There's just, argon, argon, argon. So we've got 4 macrostates. Now, if we could distinguish them, obviously we'd go back to our 8, right? Because we'd be like, oh, look, number 1 and number 2 are the right, all those different things. So very weird logic, but that's what we have. Microstates are when we can distinguish every particle. Macrostates are when we cannot distinguish particles. You will always have either more microstates than macrostates or an equal number. Okay? Almost always more microstates than macrostates. Okay? Why does that matter? Why do we care about are things distinguishable or not? Because real molecules and atoms are not that distinguishable, and so we do have to count things slightly differently and know what we're counting. All right, so we had 8 microstates in here. What we want to know, if we look back at our box analogy, right? What's the probability that everybody's on one side of the box? Right? That's what we're looking at. Oh, do we need to go and breathe down out of the corner of our box? No, we don't generally need to do that. And so what's the chances, what we want to know is, what's the chances that everything's on one side of the box or the other side of the box versus spread around in the box? So if we look and start counting things, right, what are the chances that all 3 of our atoms here are on one side of the box? Well, if we look at things, we have this one and this one are where it looks like it's just on one side of the box. So there are 2 different arrangements where it's on one side where all the atoms are on one side of the box, out of my 8 possible arrangements. And so that's a probability of 1/4. So there's a 25% probability that everybody's on one side, which means there's a 75% probability that these guys are distributed around the room. So if we walked into this room, about 25% of the time they'd all be in one corner, and about 75% of the time they'd be spread around. Now, we have a lot of different microstates that spread them around, right? RB and then G, G and then RB, R and then GB, right? So there's lots of different ways of arranging that one. And each one of those is just as likely as the other one, right? I didn't say there's any energy cost to going back and forth, right? They're just bouncing back and forth, and we're just looking at it at a moment in time, right? And so any of these is just as likely as any one of them, as any other one. But there's 6 different ways to spread them out of 8 possible. And so that is a 75%, 3 out of 4 chance that we're going to see them spread out. And so you can kind of see a little bit like, okay, well, in my room, there's ways of arranging it into a corner, but there's only a few of them. But there's lots of ways of arranging them spread throughout the room. But the chances, if I say, hey, what are the chances that I have red on the left, green, blue on the right? Well, that's only 1 out of 8, right? So if I'm talking about things in very exact positions, I'm saying this exactly here, this exactly here, this exactly here, then the probability of that exact thing is fairly low. But it's also the same as the probability of all 3 being on the right, RGB on the right. That's the same probability. There's one way of doing that, and there's one way of doing the other one. They're equally probable. Now, we see more often the ones where they're spread out because there's lots of different ways. So if these are all equally probable, then the system's just going to keep kind of bouncing back and forth between them. And 75% of the time, it's going to look to us like it's spread out. And 25% of the time, it's going to look to us like it's on one side of the room. So let's expand this out. Let's say we had 10 balls. 10 balls. What's the probability they're all on one side? It's about 1 in 1,024, right? That's a pretty small probability already, 1 in 1,000, that all 10 balls are going to be on one side, which means that most often when you look in there, the balls are going to be kind of spread out across the thing and not all shoved into one corner. How about if we had, and you're going to be like, why did you pick these numbers? 139 balls. If you ever played Super Lotto Plus, 139 balls is all you need, where the probability of them all being on one side is about the same as winning the lottery buying one ticket. Right? That's not very many balls, right? That's 139 balls, that's not very many. 139 atoms, and yet the probability is so low that they're all going to be on one side? Wow. Winning the lottery, that doesn't happen very often, right? I mean, somebody does, right? So you're like, oh, somebody's going to walk into a room and find gas in a corner. Well, how much gas is in a room? Not 139 balls, right? That's a lot of gas. We'll get there in just a moment. Well, turns out if you take n equals 329 balls, the probability is about 10 to the minus 99. Right? So at 329 balls, your probability is about 10 to the minus 99 that they're all going to be on one side of the room versus somehow spread out. Because there's only one way of arranging them on one side of the room, and so many ways of arranging them spread out. Right? 329 is already 10 to the minus 99. Why do I do that one? Because most calculators can't do smaller than that number. 329 balls. But in a room, how much gas do we have? Well, we know the mole volume of gas is about 22.4 liters per mole. So in a room of 22 liters, which, you know, is maybe if I made this box about this big, right? I have a mole of gas. And if I have 1 mole of balls, right, 6 times 10 to the 23rd balls, okay? What is the probability that they're all going to be in one corner? What's the probability you're going to walk into the room and have to go and breathe out of one corner? It is infinitesimal. In fact, if you have a mole of balls, the probability of them all being in one corner of the room is about the same probability as if you take every lottery ever played in the history of mankind and you buy 1 ticket for it. You win every single lottery. You're like, oh, that's pretty small probability. No, wait, there's more. So you do that every hour. So you take every lottery ever played, every hour, and you buy one ticket, and you win every single lottery since the inception of the universe about 4.5 billion years ago. So play the lottery every hour for 4.5 billion years, buying one ticket for each lottery. Oh my goodness! That's why you never walk into a room and see all the balls, all the gas in one corner. Not that it can't happen. It's actually just as likely to happen as when you walk into that room and all those balls are exactly where they are at that very moment. They have the same probability of happening. However, there's so many ways of arranging it where they're spread across the room that's all we ever see. Because the probability of us seeing that one configuration where they're in the corner is so infinitesimal as to be zero. So, right, even though these have equal probabilities, this one has lots of ways of doing. And this one has very few ways. And so our experience of these probabilities is that the one on the left is very probable, the one on the right is not very probable. And that's our experience because there's so many ways of arranging the one on the left and not of arranging the one on the right. All right, now, can we quantify this? Can we actually calculate these probabilities? And the answer is yes. And it turns out that answer is related to entropy. So entropy, which we use a capital S for, and if you remember, capital S means a state function. What are state functions? State functions are one that don't depend on path, right? If I go from here to here, right, GPS coordinates, right, here to here, it doesn't matter whether I, right, I ended up at the same coordinates at the beginning, coordinates at the end. That's a state function. My GPS coordinates are a state function. However, the time it took me to get there, if I go dink versus is not a state function. So time it took to travel, speed of travel, that's not a state function, but GPS coordinates are. Entropy is the same way. It doesn't matter how you get to your end path. You just need to know your end and your start, and you know everything you need to know because entropy is a state function. Entropy is equal to K. Now this is a little k. This is not little k from kinetics. This is not big K from equilibrium. This is another K. Why so many Ks? I don't know, because I think it's K for constant, but C, you can't. This is called the Boltzmann constant. And what is the Boltzmann constant? Well, the Boltzmann constant is by, guess who? Boltzmann. Okay. Now, it's actually just the gas constant divided by Avogadro's number, the 8.314 divided by 6.02 times 10 to the 23rd. And so you get a value of 1.38 times 10 to the minus 23rd joules per Kelvin. So it's just a number. It's just a number. We don't worry about it. Times the natural log of W. Okay. So S equals K times the natural log of W. Now what's W? W is the number of energetically equivalent microstates. And we'll talk about that in just a moment. What does it mean to be energetically equivalent? But it's literally just counting microstates. It's counting those things where we know exactly everything about everything that we need to know, right? And it says you can calculate entropy. Absolutely. Calculate the value of entropy by just knowing how many ways there are of arranging something. So entropy is literally just a count of the number of ways of arranging things. Stuff with large entropy means there's a large way of arranging stuff. Stuff with small entropy means there's a small number of ways of arranging stuff. That's all it is. Some people will tell you that entropy is all about disorder. That entropy, when there's entropy, things are disordered. But it's actually totally the opposite. Lots of entropy means there's lots of ways of ordering, not that there's lots of disorder. Now, our experience of lots of ways of ordering things is that it is disordered, and we'll kind of see that later on. But anyway, that's it. S equals K times the natural log of W. Now, how important is this equation? Well, over here is a bust, right? And it's actually the tomb of Boltzmann. And he did a ton of work. I mean, he discovered so many things in science, huge numbers of theories and laws. I mean, the guy was really, really smart, made huge contributions to science. But literally, the only thing printed on his tombstone, the only thing he wanted printed on his tombstone was S equals K times the natural log of W. Wow. He thought that was the most important contribution he made to science. So yes, this is really actually important, but also a little weird to think about. Right? How do we calculate the number of energetically possible microstates when we're talking about moles of things? It's a really hard thing to think about. But let's think about what it means to be energetically equivalent. So we're going to look at two systems. We're going to look at system A here. It's got a red ball and it's got a blue ball. Each of them have an energy of 2 joules. So my total energy in this system is 4 joules. 2 joules from the red ball, 2 joules from the blue ball, and I have a 4 joule system. Now in system B, I also have a red ball and a blue ball, but I no longer have this 2 joule state. I only have a 1 joule state and a 3 joule state. So now if I look about it, I can arrange it where the red ball's on top and the blue ball's on the bottom, and I still get 3 plus 1 is 4 joules total energy. Here, I can play it where the blue ball's on top and the red ball's on bottom, and I still get 3 plus 1, 4 joules of energy. So in system B, there's actually 2 energetically equivalent microstates. 2 energetically equivalent microstates. But in system A, there's only 1 energetically equivalent microstate. So if I were to try to calculate the entropy of these two systems, I'd say S equals K times the natural log of W. For system A, W would be 1. Because in order to get a total energy of 4 joules, there's only one way to do that, which is the way it is right there. Everybody's at 2 joules, right? Because that's the only energy level I have available to me. But on the right-hand side, if I was saying, what is my entropy? I'd say S equals K times the natural log of 2. Because on system B, there's 2 ways of arranging where we get a total of 4 joules, 2 energetically equivalent microstates. Right? So that's all we need to do. If we can figure out how many energetically equivalent ways there are of arranging things, we know then the entropy, which is really cool. All right. Because we'll figure out, right? Entropy is what determines spontaneity. So if we know entropy, we can determine something about spontaneity. And that's important to know whether things happen or not. Okay, so I've got things here for you. I've got 4 different scenarios here. Remember, people can exist in the circles only. But I want to know which of these systems has the highest entropy. How do we figure that out? Your turn, go. All right, what'd you come up with? Well, hopefully what you said, well, I know that S equals K times the natural log of W. So the only thing that varies in there is W. So I'm going to find the number of ways of arranging things energetically equivalently in these different ones. A, we already did. That's just 8 different ways. D, we already did, right? There's red, green, and blue, and 2 there's 8 different ways of arranging that one. I just put the green one over there to show a different starting state, but there's 8 different ways of arranging them. We already kind of figured that out. In C, right, you could have the red dot here, the red dot here, the red dot here, the red dot here. So there's 4 different ways. Right. How about B? It turns out B, if you work on it, you're going to get 9 different states. Okay, so 2, 2, and 2, right? That's that. And then you get 2 and 2, 2 and 2, 2. So if you do that, you end up with 9 different ways. And so it has the highest number of ways of arranging things. And so it's going to have the highest entropy. It's totally just, you count the number of ways of arranging it, that's going to have the highest entropy. And that concept is going to be important when we start applying this to molecules and reactions and things like that. Number of ways of arranging things is going to be very important. All right, how many energetically equivalent microstates are there in this system? So you're looking at one with energy levels of 1, 2, and 3 joules, and we're saying we want to be energetically equivalent to the system where there's a red ball on 3 joules, and there's a blue ball on 1 joule. And we go. What'd you come up with? Well, you said, hey, look, there's 1, but I also could put the blue up here and the red down here, so that's 2. I can't really put like, red here and blue here because that would only be a total of 3 joules. I can't put like red here and blue here because that would be a total of 5 joules. But I could put red here and blue here because that would be a total of 4 joules. And so in this case, there are 3 energetically equivalent microstates in this system. Red on top, blue on bottom, or blue on top, red on bottom, or red, blue in the middle. All of those have a total of 4 joules of energy. And so we can actually calculate the entropy of the system as S equals K times the natural log of 3. And that would give us an actual value for the entropy of the system. All right, I know there was a long introduction. Right? It's a 40-minute introduction to entropy and what it means. Hopefully you have a vague sense of it. We're going to keep applying that as we go forward and try to actually start applying it to chemical systems and try to get an understanding of what's going on in there. Thanks so much for listening. I hope you have a wonderful day.